Okay. In our last lecture, we were discussing the effect of light and temperature on photosynthesis, and I would like to mention one more point. Go back to your notes on under the heading of the effect of light on photosynthesis. There is this component of diffuse radiation that I would like to point out. This was looked at by Dr. Kriedemann again, and he found that with a decrease in the angle of the incident angle of solar radiation on the leaf surface, there's a big effect of diffuse light on photosynthesis. Now, the best way to look at that is if you have a grape leaf, and if this is the sun up here, and as the sun's rays become more parallel to the leaf, in other words, the thin edge of the leaf here is parallel with the sun's rays, then the diffuse radiation becomes more and more important. So, and then as this leaf is at right angles to the sun rays, then the diffuse light becomes less and less important. So the diffuse radiation is a very important component, has a very important effect on photosynthesis within the vine canopy. In other words, diffuse radiation is much of the light that's down within the canopy is light that's bouncing off the ground or bouncing off of leaves. And this is largely the light that's within a canopy. And when those rays are parallel with the sun's rays, then the effect on photosynthesis is considerable. I should also mention that diffuse radiation makes up about 10 to 15% of the total solar radiation from the sun. And now I'd like to also mention one other experiment that we did on the effect of temperature on photosynthesis. Remember last time we drew the curve and showed you the photosynthetic response to temperature. And this was derived at by using an infrared CO2 analyzer, which directly measures the assimilation or uptake of carbon dioxide. So a few years back, Dr. Leiter and myself did an experiment in the phytotron where we grew potted vines at different temperatures at 20, 30, and 40 degrees centigrade. These potted vines were started from rootings. We grew them for a month, then measured their leaf area, then put them in the phytotron at these 3 different temperatures, and then measured the gain in dry matter after a 30-day period, and again measured their leaf area. And when we did this, we found that the maximum increase in dry weight was at 30 degrees centigrade, 86 degrees Fahrenheit, with a sharp decline on either side of this temperature. This was under high light. Now light intensities that exceeded or were around about 5,000 or 6,000 foot candles. Under the low light condition, which the light intensities were less than 500 foot candles, we found our maximum increase in dry matter was at 20 degrees centigrade. Now this information is also on the handout that you received last time, that one-page handout. This is just another way of expressing that data that's on that handout that you received last time. So at least using this whole plant technique of following the accumulation of dry matter, we came out with about the same results as the Australian workers did using the infrared CO2 analyzer. Now let's go on and talk about some of the other effects of some of the other factors on photosynthesis. Another factor that influences photosynthesis is, of course, soil moisture. And this probably can best be seen if you plot this curve on the board like this. If you on this axis, this is photosynthesis again. And these will be in terms of relative units from 0 to 100%. And leaf water potential. Now don't get this confused with soil potential. We're talking about leaf water potential down here. And this is in bars, atmospheres. This is in terms of relative photosynthesis. In other words, from 0 to 100%. And we go from leaf water potentials here from 0 up to 20 bars. This would be 0, 5, 10, 15, 20. And we find that the vine photosynthesizes here at about 100% until you get up to about 13 to 15 bars and then takes a sudden plunge. This was done for 2 varieties, Thompson Seedless and Shiraz, which is much similar to that black, to our, well, their Shiraz is, I forgot. It's a different variety than ours, but it's somewhat similar to our Petite Syrah, I think. Anyway, they found this decrease occurred somewhere between, sorry, I got that drawn a little bit wrong there, somewhere between 13 and 15 bars. The photosynthesis decreases very sharply, and it's at this point where the stomatas begin to close up. Now this is a very high leaf water potential. Many plants start to close up their stomatas when they're down in this area here. So this is one of the reasons why a grapevine is so drought tolerant. It's able to photosynthesize at relatively high leaf water potentials or under very dry moisture conditions in the soil. In fact, to get these vines to this point, they had to do some root trimming where they went through with a plow and pruned off most of the roots. And only when they were able to do that were they able to get the leaf water potentials in these plants to this low level. So Dr. Cook was right in that you very, very seldom ever see a vine, quote, wilt in the vineyard. It usually has a mechanism there of closing the stomatas, and then it doesn't wilt.
Dr. Kliewer?
Yes.
Could you explain leaf water potential?
Well, the way this is done is, I don't want to take a lot of time on this, but I use this pressure bomb technique where they take a leaf off of the vine and put it under a sealed chamber thing, and then they have a tank of air sealed onto that, and it's hooked up to a pressure gauge, which is calibrated in atmospheres. And when they have to put so much pressure on this leaf to get a little bit of water to exude out of that leaf petiole. And this has been calibrated in leaf water potentials. And when that leaf water potential, in other words, when the atmospheres of tension that's required to exude a little bit of water out of that leaf reaches about 13 to 15 bars, then it's at the point. There've been also some very nice work in the last couple of years to show that one of the compounds that controls this closure of the stomatas is abscisic acid, and they found that the abscisic acid goes up very sharply at about the time that the stomatas begin to close. And also should be pointed out, once these stomatas do close, it takes several days for them to open again. So there's a loss in photosynthesis over several days, even if you immediately go back and water again. Okay, let's then talk about the effect of leaf age on photosynthesis. This is on your handout that you received last time. There's a figure there in the back. In this work, again, we measured the photosynthesis with leaf age, and this is counting from the time that the leaf first began to separate from the apex. First visible separation of the leaf from the apex was what we call leaf age 1 day old, and then from there on out. So we found that this is 35 days, 70 days, and we found that the maximum rate of photosynthesis, this is photosynthesis here now, I think this went up to about 20 milligrams of CO2 fixed per square decimeter per hour. So this is CO2 fixed per square decimeter of leaf surface per hour. And this increased to a maximum about 35 days, and this is about the time when the leaf is first fully expanded. So at this point, it reaches a maximum rate of photosynthesis. It remains pretty high up here for a couple weeks, and then gradually begins to decline. We only carried it out to 70 days in this work, but this presumably continues to decrease at a very slow rate until the end of the season, since we found that yellowing senescing leaves reach a level of about 1 to 2 milligrams of CO2 fixed per square decimeter per hour at the end of the season. So I'm sure there's just a rather slow decrease in photosynthesis with leaf age. But the point is that we have our maximum rate of photosynthesis at about 35, or say between 30 and 40 days after the leaf first separates from the shoot apex, and then it begins to decrease. Now, one curious thing that has also been noted that this absolute level here changes during the season. In other words, they found that during the months of May and first part of June, they can reach levels of 20 or so milligrams of CO2 fixed per square decimeter per hour. But later in the season, say a leaf that is 30 days old in August or September, the absolute levels there were only about 10 milligrams of CO2 fixed per hour per square decimeter. You get that point early in the season, the level of CO2 fixed per square decimeter per hour is much higher than later in the season, even though the leaf is at the same age. And we don't know the reason why this is so, but I think it may be related to photosynthetic demand. There's a much greater demand for photosynthesis early in the season when these shoots are rapidly growing, and this may have something to do for this. Now, another factor that affects photosynthesis is the size of the sink, and by a sink I mean a sink is any part of the vine that requires more photosynthesis than it can utilize. In other words, the shoot tip is a sink. It requires a lot of photosynthesis. The berries are a sink. The roots are a sink because they require more photosynthate than they are producing. So another factor that affects photosynthesis is the size of the sink. And this can be illustrated by these data. The control, where there was nothing done to the shoot. Another one where the tip was removed, so you removed a small sink. Tip of shoot removed. Another one where the tip is present, but the stem has been censured, or a little ring of girdle put around it. So stem censured. And then the tip absent, and the stem censured. And the rates of photosynthesis here, again, this is in milligrams of CO2 per square decimeter per hour, were 19.9. Sorry, the control was 19.9. When the tip was removed, it was decreased to 18.9. But the big decrease is here where the stem was censured. It was 13.1, about a 34% decrease compared to the control here. And then it was 12.1 here. So this suggests when the stems are censured, this is eliminating the eliminating the roots as a sink. In other words, the photosynthate for the roots has to come from the above ground parts. So when you make a ring or a girdle around the stem, you've eliminated the roots as a sink. And this indicates that the roots have a much more important effect on regulating the rate of photosynthesis than when the tips were removed. Or maybe you could say that the roots are a much bigger sink than the shoot tips. And remember, the roots are completely dependent on photosynthate. They do not photosynthesize at all. The shoot tips do photosynthesize always to some extent, although part of their time they're not photosynthesizing enough to take care of their needs, but at least they're photosynthesizing to some extent.
What do those data mean exactly? CO2 fixed or
milligrams of CO2 fixed per square decimeter of leaf area per hour. These are the units that have been used in all these graphs here, except this one here where they are in relative units here. But this is the way that with the infrared CO2 analyzer work, they've always measured their photosynthesis as milligrams of CO2 taken up per square decimeter of leaf area per hour. Now the Vitis species, the species of Vitis also can affect photosynthesis. There's been one paper indicating that the CO2 assimilation rate of Vitis vinifera and Vitis rupestris were about twice that of Vitis labrusca. And this is a rather old paper. I think that should be repeated and reconfirmed, but I'll just throw that out at you. In this one work that was done by some German workers about 15 years ago, they noted that the photosynthesis was going on at a rate about twice as high in Vitis vinifera as it was in Vitis labrusca species. Now let's go on to another topic. Let's go on to look at some of the effects now of light intensity and temperature on bud fruitfulness. Just take a few minutes on that, and then we'll go on to carbohydrate nutrition work. Now, there's been some very nice work in the last several years on studying the effect of light intensity on the number of clusters primordials per bud. This work has been done using plant growth chambers where potted vines were put into very controlled environments and the light intensities were varied, and then they sectioned each bud on the shoot and counted the number of fruit primordia being initiated at these different light intensities. And this can best probably be seen on that slide there that we have. There's an increase, there's a linear increase in light intensity. I think we can leave the lights on here. We're just going to show this one slide now. There's a linear increase in bud fruitfulness with an increase in light intensity between 900 and 3600 foot candles. Can you all see that in the light? So in this experiment here, which was done in controlled growth chambers, there was an increase in light intensity from 900 foot candles to 3600 foot candles for these, looking at these three varieties. And you can see there's roughly a linear increase in the fruit primordia, which are rudimentary fruit clusters, with an increase in light intensity. And the mechanism here was explained in terms of photosynthesis. With an increase in light intensity, there's an increase in photosynthesis, which would mean there would be an increase in carbohydrates. And this resulted in an increased fruit bud initiation. This also now is on your handout, I believe. Now we might as well show that next slide there.
It might be a significance, or is it, that white Riesling?
Well, that might be worth mentioning, that the white Riesling had the highest fruit primordia per bud at all light intensities. And remember that this is a variety that's growing now in Europe under relatively low light conditions. So that might be significant, although I'm not sure how it would turn out under statistical analysis. Now this shows the effect now of temperature on fruit bud initiation. We're going, I think, is that in focus? It's not in.
I think it's this thing getting loose out here.
Yeah. Well, anyway, we're going from temperatures now from 15 up to 35 degrees centigrade, which is 59 Fahrenheit up to 95 Fahrenheit. And this is primordia per bud. And again, we see that there is a for most of these varieties, there was roughly a linear increase, or at least an increase in fruit primordia per bud with an increase in temperatures. For this one variety, this variety is Rhine Riesling here that reached its maximum at 30 centigrade and then began to decrease. The others were continuing to go up until 35 centigrade. Now these two varieties, one of these is Thompson Seedless and one is Onez, I think, which is Almeria. They had relatively low bud fruitfulness at all these temperatures. But this at least shows that there is a very marked effect of temperature on fruit bud initiation. And this, well, I should also point out that, and this is rather surprising, that there was absolutely no buds being formed here for this Gordo, which is Muscat of Alexander, when the temperatures were at 20 degrees or less. When temperatures were held at 20 degrees centigrade or less, no fruit buds began to form. Now this had to be about 15 degrees or less for these two wine varieties, Rhine Riesling and Shiraz. When the temperatures were maintained at 15 degrees centigrade, 59 degrees Fahrenheit or less, no fruit buds were being initiated. So it indicates that also that these wine varieties are able to initiate fruit primordia at lower temperatures than these table varieties. And also we noted that the light intensity required was less for the wine varieties. So this could help explain why some of these basal buds on these wine varieties tend to be more fruitful than some of these table varieties, perhaps. Another piece of information that they found in this study is that it required 4 hours of these temperatures to get the maximum fruitfulness. And they could give that 4 hours of temperature any time during the day or night. As long as they had 4 hours, say, of 30 degrees centigrade, this was sufficient. They did not get any improvement in the fruit.
That's just 4 hours a day or 4 hours a day?
4 hours a day. Now that could come during the day or the night.
How many days?
And this was done over a 3-month period. But it was interesting to note that 4 hours of that temperature, of any of these temperatures, was sufficient to give the fruit buds being initiated. See, that's all the slides, isn't it? Yeah. Now, Dr. Leiter and myself did some experiments here with the Thompson Seedless vines a few years back, where we looked at the effect of cane position on bud fruitfulness. In other words, we went out and into the vineyard and selected what we considered to be sun canes or shade canes. Now, I think we talked about this to you in our pruning. And these types of canes have been defined to you as a shade cane is a cane that tends to be rather spindly, very long internodes, and you can pretty well tell these by their position during the dormant season. Well, we went out and compared then and pruned vines to what looked to be to us shade canes and sun canes, and then during the following years we then counted the number of clusters per node and weighed the number of fruit per node and calculated the percent bud break on the vines. And these are some of the data that we found. Now this is for Thompson Seedless vines, and we're going to compare now sun canes and shade canes. Number of clusters per node. And this is just another term for bud fruitfulness. Number of clusters per node is bud fruitfulness. We found on an average 1.22 clusters per node on the sun canes and 0.98 on the shade canes. Average cluster weights were 0.88 pounds for the sun canes and 0.78 for the shade canes. Percent bud break, percent of the buds that broke. Was sorry, that should be 85% here and 80% for the shade canes. And bricks was degree bricks was 20.6 and 21.2. So not a very big difference there, but there was a very marked difference here in the number of clusters per node. Now we also did this for Gamay Beaujolais at Oakville. This is Gamay Beaujolais, and it found almost the same results. 2.01 clusters per bud for the sun canes. This is sun. This will be shade. I don't know if we're going to be able to see. Can you see that down there or not? Can't? Well, anyway, we had 2.01 buds or clusters per node for the sun, 1.32 for the shade. Average cluster weights were 165 pounds and 160 pounds per cluster. Percent bud break was 84% and 72%. And degree bricks was 25.6 and 25.1. So the canes that you select during pruning time can have a tremendous effect, and the main effect was now on the number of clusters per node. On the Thompson C list, there was an effect on cluster weight and a slight effect on the percent of buds that broke. With this Gamay Beaujolais that we did at Oakville, again, there was a very marked effect on the number of buds per on the number of clusters per bud. A little effect on the cluster weight, but then a significant effect on percent bud break, 84 versus 72. A relatively little effect on fruit maturity.
Is that the normal sort of cluster weight for Gamay Beaujolais? That's pretty small.
Yeah, it's a small clustered variety, Gamay Beaujolais. So I would say this is about in the normal range.
Was there any effect on shoot growth?
We didn't measure the effect on shoot growth. Now, we did take this a step further for the Thompson C list vines, and I'd like to show you that data very quickly too. Now, this will show you the effect of node position on the canes, and here we have node position. This is now an average of about 20 canes. We had node positions 1 up to 20. 1, 2. These are node positions now. One, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's far enough. Now, then we have this again: sun canes and shade canes. And we counted, this is for 10 canes now, and we counted the number of clusters at each one of these node positions. For node position 1, there was 0 in both of them. For node position 2, we had 5 clusters here, and 0 for the shade canes, 7 and 5, 9 and 6, 14 and 6, 15 and 9. For the 6th position, 14 and 8, and 16 and 8. And this is kind of a breaking point here. After about node 9, there was relatively little. There's much less difference between the two then. 14 and 12, 11 and 10, 12 and 16, 15 and 10, 15 and 19, and so forth. But the main point is that on the first 8 nodes here, there was a rather marked effect on the number of clusters per node position. And it's these first 8 nodes that were in the shade during the entire growing season. Once you get beyond about the 8th or 10th node there, the ends of these canes are growing out into the sun, and then this was out of 10. This was out of 10. This is an average now of 10 for 10 canes. So there's a marked effect of node position on bud fruitfulness, and this is mainly an effect of light intensity hitting these basal nodes. Once the canes get further out on the vine, they're into the sun, and then there wasn't nearly as much effect on number of clusters per node.
That's the total number of clusters per 10 canes.
This is the total number per 10 canes. So here we had 5 out of the 10, 7 out of the 10 had clusters, 9 out of the 10 had them, and so forth. Here we had more than an average of 1 cluster per node position, 14 out of the 10. Okay, I think that's the main things I wanted to say about the effect of temperature and light on bud fruitfulness. Now let's go on now under a new heading and start talking about carbohydrate, nutrition, and utilization. And this subject was touched on very briefly in 116a when we talked about dormant pruning. And we talked about how the sugars and starches can interconvert from one to the other. During the cold dormant period, we drew that curve on the board where we showed there was a conversion of starch to sugar and sugar to starch during the winter months. I would want to interject one thing here now. In the roots, at least in the roots below about 6 inches, there's probably no interconversion there of starch to sugar, since the temperatures seldom go below 45 degrees Fahrenheit in the soil, below 6 inches in depth. So the roots in California, at least this is for California now, this might probably be true in Washington or Europe or somewhere, but in California there's probably little interconversion of starch to sugars. Now, the first thing I'd like to show you is the seasonal changes in the carbohydrates that occur in the different parts of the grapevine throughout a one-year cycle. And let's now first look at the general values for the maximum and minimum amounts of carbohydrates. Carbohydrates here being sugar and starch in the woody tissues and in the bark. Now, on woody tissues, now, I should also put on a reference here. This work that I'm going to be talking to you now about is a very classic study that Winkler and Williams published back in 1945. The reference on that is, this is Winkler and Williams. And we used to sign this as reading, but I don't think we're going to do that now. And this is titled Starch and Sugars in Vitis vinifera. And this is Plant Physiology. Volume 20, page 412 to 432, 1945. This paper is cited all over the world, and it was really a well-done piece of work for that time. It's a little bit confusing to read, but I think if those of you who want to get a better understanding of this subject, we can put a couple of these in the Winkler Library, and those of you who would want to read that would be welcome to do that. The way the data, though, is expressed, it's expressed on a sugar and starch-free basis. In other words, they expressed it on their data. Most of the data in this type of work is expressed on a percent of a dry weight. Well, Winkler and Williams, they subtracted their sugar and starch so that the percentages that you find in that paper tend to be higher than you would normally read in many papers. In other words, if you had one gram of starch and you had 0.25 grams of sugar and if you had 1 gram of dry matter and you had and this contained 0.25 grams of starch and sugar, they subtracted this 0.25, which gives you 0.75, and then they expressed it as a percent of that, so it's 0.25 over 75, or 33% carbohydrate. Well, normally this would be, in most papers, this would be 0.25 over 1, or 25% rather than 33%. So the carbohydrate values are very high in some of these tissues, and it's partly because of the way the data were expressed. And one other point that should be mentioned in this paper is that the work was done with Carignan grapevines between 1 and 4 years of age, and all the fruit clusters were removed. So these vines were fruitless varieties, and this probably may also have I'm sure would have an factor on the carbohydrate levels if they had fruit on them. But there is a lot of information that came out of that paper, and I'll pass some of that on to you now. Now let's look at some of the general values for the maximum and minimum amounts of carbohydrates in the woody tissues. These are woody tissues. And for the canes, we'll look at 3-year-old trunk wood. One-year-old root wood. And the rootlets. Rootlets now are very small roots, less than 3/32 of a diameter. And this is now these first 3 here are the woody tissues only, which is mainly the xylem. And the rootlets included the wood and the bark. And the high during the dormant season in these this is the high level of carbohydrates in percent was 18 to 22% for the dormant cane tissue. The trunk wood had anywhere from 20 to 25%. The 1-year-old root wood had 30%. And the rootlets 50%. And the low level in their yearly cycle was 6 to 8%. And the month was June. 18% for the 3-year-old trunk wood. This was June to July, end of June to July. The 1-year-old root wood had reached their low of 5% in June through September. And the rootlets reached down to 15% in August. Now this sentence to suggest that the carbohydrates from the canes were first being used. They generally reached their low of 68% in the early part of June. In the trunk wood, it was usually a little later, in the end of June, July, reaching a low of 18%. And note that not nearly as much of the trunk wood was utilized as it was in the cane wood. In the rootlets, they reached a low, well, it was rather a broad range there from June to September. And the rootlets also reached a low in August. Now in the bark tissue, which is really the first tissue in which the carbohydrates are utilized by the new shoots in the spring. This is be the same now, but under the heading of bark tissue. And here we have the base of the canes, trunk, and this was the 3 to 4 year old trunks now. 2 year and older roots. And 1 year roots. And these are now, this is bark only. For all these, it's bark only. The high was, this is carbohydrates. The high carbohydrate was, I sure don't have much good chalk up here. The high was 18% for the cane bark. This is the basal cane tissues. And the low was 4% in June. The trunk had a 25%, reached a low of 4% in June. 2 year and older roots had a high of, the bark had a high of 50%, reached a low of 8% in August. And the 1 year old roots had 85%. In fact, they were the highest of all the tissues. 85% carbohydrates, reached a low of 25% in August. So the bark tissues, at least in the roots, tend to be extremely high in carbohydrates. The woody tissues in the roots are quite a bit lower. And I should also mention that most of the carbohydrate is present in the form of starch. In fact, usually only 2 to 3% of the total carbohydrate is in the form of sugars during most of the season. So most of the carbohydrate is present in the form of starch. There may be a stage in the shoots where the sugars reach a level of 5-6%. Right around bloom time, but mostly the sugars are present in a level of 1 to 3%. And the carbohydrates are translocated as sucrose in the phloem tissue. Most of it is translocated as sucrose. There's a very small amount that's translocated as raffinose and stachyose, but by large the bulk of it is translocated as sucrose in the phloem. Yeah.
Could you stop at that point? Let me have a couple minutes.
Yeah.
I've got a handout up here for you, which I forgot to get out in Diffusion. This is a little article that was published in a little magazine called Vintage, and I think it's worth your reading. It's called Evolution of a Vineyard. And I read through it. It's pretty well written, and it covers the subject pretty well of what you've had so far in the course. But in reading it, before rather quick myself, I found at least 13 points where you're either wrong or you're right. this, in which you can debate and argue whether or not the correct statement is really correct. This is a take-home quiz. I want you to give me 7 of those 13 that I found. 2 points apiece. Wednesday, turn this in Wednesday. Or it'll take you all of 10 minutes to read. I want 7 of my 13. You can put down as many as you like, but I want, if your first 7 are not among the 13 I found, it won't count. 2 points apiece. Or you can put down as many as you like at the end of the sleep. But I found 13, all you got to do is find half of them that I found.
Are we limited at all if we find something that you haven't found?
Well, you'll get only credit for 7 points, 2 apiece. The first 7, and I'll draw the line at 7. Then we'll see how many you got below that.
You read them and maybe...
Oh, we'll discuss them in class here.
What if they put down points that aren't debatable? Will they get marked off?
Sure.
Okay.
Because this is really a summary coverage of what you've had so far in the course. And also, for those of you thinking about planting vineyards, it gives you a little bit of something that what you're going to run into. Now, we still have about 6 or 8 exams up here. Green, Allison Green. Brandon. Mandavi. Dakota.